My talk, as Chivi said, is going to be on energy storage to support renewable generation. I'll begin with a quick introduction to the kind of stuff that I do, and then move on quickly to give you an outlook of the renewable energy worldwide. And I've kept this presentation, the content fairly broad, because I expected a broad audience. So when I do talk about reliability, I'm going to try and give you a sense of how we use reliability and how it is a probabilistic measure. And then I'm going to talk about variable generation, which is most the dominant renewable generation that we have on the grid today is variable in nature. And I'll talk about what that means and the challenges that arise from it. In particular, I'm going to talk about ramping rates and ranges, how we mitigate variability and its impact on frequency stability. And then I'll come to the central theme, how can we deal with some of these issues, some of these challenges using grid scale storage? And can we actually size storage accordingly? If you have storage is an expensive asset and you have to size it appropriately to make sure it meets the objectives of your mission. So with that, here's a brief introduction to myself. I'm not going to read all of this out to you. The logo that you see on the top right is the logo of my lab, the Energy Reliability and Security Lab. And this is one of the many logos that Michigan State uses, the one on the top left. And I'm mostly known in the community for my contributions to reliability and reliability-based planning, but I've also done a lot of work related to stability and security, not as much cybersecurity, and though we old timers mean something else when we talk about power system security, but and these concepts are re-emerging today in the context of this new buzzword that we have floating around, right? Resilience. And I like to begin my talk by acknowledging the contributions of my former students who have contributed to the body of work that I'm about to present today. So this is the subset of students who have contributed to the content that I'm going to present today. So I'm going to start talking about the growth of renewables and point certain things out to you folks. This is how renewables have grown in the last 20 years. Well, as much as the last 20 years and then last 10 years, as much as the last 10 years. And in 2020, I wasn't able to find enough comprehensive data since 2020. So I'm sticking to the 10 years that ended in 2020. What I want to point out first of all is how non-hydroelectric based renewables have grown. And you'll see that their growth has been quite dramatic. Yes, hydro resources have also grown, but not nearly as much, because we've always had hydro, right? We've always had hydroelectric as a renewable resource. Indeed, today we think of hydroelectric as being less renewable in the sense of their environmental impact than we used to before, because we've realized that submerged vegetation can contribute to greenhouse gases as they decompose, and it has impact on aquatic life and things like that. So people are questioning if a hydro is an environmentally friendly resource, but I'm afraid it's here to stay for a while, regardless of whether we get into these contentious issues or not. This line that you see here shows how much it has grown in 10 years. Again, talking about non-hydro renewables. In 10 years, it's grown by from 20% to almost 30%. So that's a significant rate of increase, and we'll see more of that here, where it shows the trends over the 6 years leading up to 2020. And what you'll notice is 6 years ago from now, that is about 2016, solar overtook wind. Before that, wind was the dominant renewable resource. But in 2016, solar overtook wind, and solar has its own characteristics, and we'll talk a little bit about wind and solar characteristics. Okay, and if you look at the installed capacity in gigawatts, year by year, biopower, geothermal, ocean power, and CSP stands for concentrated solar power. Okay, they have, sort of ebbed and flowed. Okay, in 2020, not much was installed, but in the couple of years before that, quite a bit of it was installed. So all those are being deployed, but you can clearly see that wind and solar have been the dominant renewable resources, and they share certain characteristics that I'll talk about later. They also have enough differences. I also want to talk about some of the phenomena that have influenced the energy outlook, okay, and how politics has played a part in it. So we know that there's been a lot of pressure in recent years to reduce coal generation, not just because they create a lot of pollutants, both gaseous and particulate pollutants, but also have an adverse impact on health. So there's been a lot of pressure to reduce coal. But if we do away with coal, what is going to replace our base load generation? And why is base load important? Because it is an important aspect of reliability, okay? And a lot of people, including myself, forgive me if I tread into contentious territory now, think that nuclear, we should be seeing and building more of nuclear today. But unfortunately, the Fukushima event gave rise to some fear of nuclear generation that has persisted, and what is going on now in Ukraine has not helped matters. But many people do believe that nuclear should take up a large part of our, significant part of our portfolio if we want to provide reliable energy service, electricity service to the country. If we have to maintain the levels of reliability that we've gotten accustomed to. Another thing that some people might find contentious, but I really think that if you stop to think about the impact of markets, I think their focus on economic and financial profits have undermined operational efficiency from an engineering perspective. It's the difficulty in coordinating both planning and operation, in an end-to-end manner, has affected reliability of the system, and that has manifested itself in many different ways in recent times. But unfortunately, we have started walking on a path that we are not able to turn around from. Yet another factor is that the discovery of shale gas in America has influenced the resource mix quite a bit and redistributed the global petroleum economy, our dependence on the OPEC countries. And I'm sorry is that my computer that keeps putting out these notifications? It would take too much time to stop that, so I'm going to ask you to bear with it. Let's talk a little bit about some of the operational challenges in renewable energy integration. Most of you are aware that resource variability is also known as intermittency. Okay, or the new word is stochasticity of these resources like wind and solar poses a challenge in integration. When wind picks up, for instance, that means that other generators need to back down, conventional generators. And when wind drops off, they need to ramp back up, and they have to do it quickly so that we don't lose load in the meantime. not all generators have this kind of ramping capability, but enough for now. I'm going to talk more about ramp rate and ramp range on a later slide. Another thing that we've seen is reduction of regulation capability and the increased need for frequency regulation, and I'll talk a little more about that too later. But I just wanted to mention these things up front, okay? So you're prepared for what's coming. There's been a decrease of base load, and there's been an impact on base load generators as a result of integration of all these renewable resources and the efforts to integrate them more effectively. So I have yet another slide to talk about them. So let's start with the topic of variability. For those here, let me get rid of this bar on top. Hide floating controls. Okay, I think that's better. So let's talk about the variability of wind and solar. Now, wind and solar are variable because the underlying resources, which is wind speed and solar radiation, are subject to the whims of nature. We have no control over them. So the other term that you'll hear in this context is non-dispatchable. Dispatch means you need some power, you have send out a command to a generator to produce that much power, and it does that. But you can't do that with wind and solar. So they're called variable or non-dispatchable resources. Now, wind and solar behave differently, though. You'll see that wind is not very well correlated with load. That load goes up during the daytime and drops during the nighttime. And how many times have you noticed that wind, on a hot summer afternoon, when you need the wind the most, not just to turn your wind turbines, but also to cool things down so the load on your air conditioners is less, okay, that's when the wind decides not to blow, right? And in the evening, when you don't need it as much, that's when you encounter the most wind speed. So it's not very well correlated with load. And the fact is that that does cause certain operational challenges in that you have to ramp up and down. And I'm going to explain that in a minute. But there's also this matter of low capacity credit or capacity value. And when I introduce a term like this, I like to, okay, because I moved away from that, I need to click on the screen or it won't respond to my, yeah. So I like to provide a definition of capacity value. Okay, so while you're reading this, I'm not going to read this out to you. I'm going to give you yet another way to visualize the numbers. So let's say there's a wind farm of nameplate capacity 100 megawatts. That is, if you look at the peak capacity of all the turbines on that farm, you and add them up, then they add up to 100 megawatts. That's the nameplate capacity. Okay, it could have a capacity value of 20 megawatts or 25 megawatts, and that's typical of onshore wind. What does that mean? We've talked about wind not being dispatchable, but if you had to replace it with a dispatchable resource that would produce power, like combined cycle plants or something, okay, that would produce power, as much power up to its capacity as when you needed it to, then you could replace a 100 megawatt wind farm with something like a 20 or 25 megawatt conventional generator, because you can count on that, whereas you can't count on this, right? So that should give you a sense of what the capacity value is. So then that 100 megawatt wind farm would have a capacity value of 20 megawatts or 25 megawatts or thereabouts. And that's an important planning metric because capacity value depends on a lot of factors. What the location is, both geographically in terms of wind availability and consistency of wind. For example, offshore wind will give you more consistent wind speed, so the capacity value is higher. Okay, at the same time, the other location-related aspect is location with respect to the grid. How well interconnected is it with the grid? If it generates 100 megawatts consistently, a lot of the time, not 100%, maybe not 100%, but a lot of the time with the grid and the interconnection, permitted to absorb the 100 megawatts entirely? Sometimes the answer is no, and you do what is known as spillage of wind, okay? And so that should give you a sense of what is capacity value. Now, solar behaves a little differently. It shows better correlation with load because loads are high during the daytime, and the sun is up during the daytime. The solar radiation gets stronger as the load gets higher, so that helps. Okay, and but we know for sure it's not available in the night, so we can't be too dependent on it. We have to make alternative arrangements for when it's not available. The lower variability and higher predictability than wind can help, coordinating with conventional generation. And also, there's this option. You can combine it with thermal storage, like molten salt storage. And many of you know that in Arizona, they've got a few concentrated solar plants with molten salt storage. That makes its dispatchability a little better, so to speak, a little more dispatchable. And we'll talk about just how much storage, later on, we'll talk about just how much storage you need to make it fully dispatchable. So this graphic gives you a sense of what variability means in wind and solar. So these are the outputs of two farms, one wind and one solar. So the blue curve is wind farm, but it's a 150 megawatt wind farm, whereas the solar park is 24 megawatts. Now they are both located close to each other in California. And by the way, I pulled this graphic out of this report that I've cited at the bottom of the slide. And I want to tell you that most of these reports that I cite in my slides you can just use your internet search engine to find these reports, and they are available for free, okay, if you need to dig more. So note that they are different sizes, so they are on different scales. The left side scale is for wind, and the right side scale is for solar. And you can see this pattern, and I know some of you are wondering that is it possible to co-locate two identically sized wind and solar farms and sort of reduce the overall variability? Theoretically, yes. Okay, it can help. Okay, especially if you assist it with other devices, and that is absolutely a possibility. Let's talk a little now about some of the impacts of variability where it comes to dealing with, how the system has to deal with it, how the rest of the system has to deal with it. So this graphic is out of this resource that I've cited at the bottom, the NREL report, the report from National Renewable Energy Lab. Okay, and what it shows is the blue curve is the load, and you can see the daily cycles, high during the midday to early afternoon period and low during the night. So this is a 2-week period, as you can see. So here's 1st April to 15th April. So there's a 2-week period, and you can see it shows a certain level of variability, which we expect. Okay, so this is, these are the peaks and these are the troughs of the load curve. Okay, and here's the wind. Notice how the wind is almost negatively correlated with the load, right? The load is low here, the wind has picked up, okay, in the nighttime. So now, in this simple example, what they have done is they've modeled the wind as a negative load. That is, if you assume that the entire wind production can be absorbed by the grid, then you can think of it as a negative load, right? You can basically subtract it from the total load to see how much remaining energy will have to be pulled from the rest of the grid, from conventional resources. And that's what the green curve does. So the blue curve minus the red curve gives you the green curve. Okay, and they are calling it the net load. That is the amount of load the conventional resources on the grid will have to pick up. And you will immediately note note that the difference between the peaks and the troughs has increased here in the green curve in comparison to the blue curve, right? That is called the ramp range. So conventional generators have to ramp up from this end, or if you look at this part, okay, from this trough to this peak during the course of this half day. Whereas without the wind, it would have only had to ramp up from here to here. So the ramp range has increased, which means you now need more generators that have the capability of ramping up as rapidly. Not all generators can do that. So all of a sudden, in places like California, you know, the generators with ramping capability are now traded on the market with at a premium. Okay, so the rate at which you have to be able to ramp up and down, that is called the ramp rate. And you can see what the ramp range means. So that is a problem or a challenge associated with variability, right? How do we mitigate this? So at this time, there are three approaches to mitigating it. So you mitigate the temporal, you take advantage of the temporal diversity by using storage. Okay, so when you have a little surplus, you store it. When you have a little shortfall, you discharge the storage device. And so you can smooth out the variability that way. The other is geospatial diversity. And there's a very simple way of thinking about it. Let's say you need power in Houghton, but the wind power in Houghton, but the wind speeds here aren't high enough. And if they happen to be higher in Chicago, and if you have a strong interconnection between here and Chicago, you can get any excess that they might have in Chicago. Chicago won't have any excess, right? Oops, bad example. So, but you get the point. You know, you could import that to Houghton. Maybe we can turn that the other way around. If they need power in Chicago and there's wind speed in Houghton, we can export some to them and make money out of it, right? Okay, but you need transmission, okay? And flexible loads, this is a new paradigm that also needs, you know, smart grid technologies. And you can see that all of these, I'm not talking about this yet because I'll explain that a little more on a later slide, okay? But you'll see the need for smart grid technologies. And here I've shown some of the ramifications, some of the relationships between the technologies that we use and the cost. For example, okay, if we had to deal with this using transmission alone, or, you know, what I call aggregation. So in 2007, the National Renewable Energy Lab ran this study, okay? Again, this is the title of the report, DOE, DOE report, 20% wind by 2030, okay? They ran this study and said that we'll need over 12,000 miles of new transmission if we have to accommodate 20% wind by 2030. So what you see in this graphic is the green lines are existing transmission lines, and the red lines are locations where you would have to put a new transmission. And this is the amount of transmission you would need if you had to deal with this much extra wind using aggregation alone. Now, are we going to do that? Well, yes and no. Our target is moving, and we may need a balance of all three means of variability mitigation to absorb it. Okay, but we'll definitely need transmission. And I have to tell you that even though that study is 15 years old, many of these lines have been built. Okay, and oh, I forgot to mention that this construction was going to cost $20 billion, and eventually it'll end up costing a lot more. Okay, and I know half that money has already been spent. Okay, you don't need to take pictures of this, because if you want, I can just send you the slides. That's not a problem at all. Just email me. Okay, so here's the third approach, that is generation following. And I want to explain that by starting out with today's paradigm of power system operation. We call it load following. What do we do? So see the envelope of these curves, this resembles the daily variation of load that you've noticed, right? So this is indeed the total load as it varies throughout the day over, say, a span of 1 week, okay? And what we do in power systems today, in the grid today, is load following. That is, people are allowed to switch their loads on and off at will, and we have set up controls that allow the generators to track this load. So there's base loading generators, okay, mostly coal and nuclear and things like that, that run 24/7. And when beyond the base load, they vary a little bit. That is picked up first by what are called intermittent generators, okay, intermediate generators, and then by peakers, okay. And a lot of these peaks could be picked up by wind and solar and other renewables, but otherwise, we also use small gas turbines and diesel generators to do that. But this is the conventional approach to balancing generation and load. But there is a school of thought that says we are migrating toward a generation following model where we don't have control over the generation because I said it's non-dispatchable, right? So we let the resources be available whenever nature chooses to make them available, and then we control our loads to track it. So that will allow us to absorb more solar and wind, as you can see. So this green part is solar and this blue part is wind here, okay? So this is what our generation profile is going to look like in a generation following world, okay? Now look at the impact on base load units. Okay, if that happens, it is going to negatively impact your reliability. And people are already concerned about that. So as I said, as we move toward a future, we will likely strike a balance between these three approaches to accommodating more variability. Okay, so let's quickly take a look at some energy storage systems and their characteristics. So on the left, you see the different storage technologies. CAES stands for compressed air energy storage. SMES stands for superconductive magnetic energy storage. Okay, and what you'll note is that the most viable form of grid scale, that is several hundred megawatts available for several hours at a time, it comes from pumped hydro. This is the only mature, economically viable storage technology that we have that allows us that. Okay, the others are all much shorter term and much shorter in capacity as well. How has storage grown? So over the 29 to 2020, it's grown by this much, 7 gigawatts, which is not insignificant, okay? And this is worldwide, okay? And how are they composed? You'll note that pumped storage, not surprisingly, is still more than 20%, 90% of the total storage portfolio that we have today. And you all know how lithium ion has been growing. So it's grown from 4.6 to 6.9%. But realize that lithium ion is a kind of battery storage technology that is not really suited for grid scale. Okay, it's being deployed mostly on distribution scale, a few megawatts. You won't see lithium ion installations going up to hundreds of megawatts. But there are some other storage technologies like flow batteries. Okay, there was a time when we thought that sodium sulfur, which, we had a few sodium sulfur facilities in the hundreds of megawatt range, but now because of materials and environmental impacts that is being phased out, we are hoping that things like vanadium redox will pick up. Okay, in the United States, we don't have any large vanadium redox capabilities yet, but in a couple of years ago, In China, they built a 200 megawatt to 800 megawatt hour vanadium redox facility near Dalian. I don't have data for that yet to assess how it's been performing, but that was a bold step, and I wish we could do something similar to play around with and learn a little more than that about. But we are investing a lot in vanadium redox. Yes.
Vanadium, is that an element?
Yeah.
So my lack knowledge of chemistry. Where do you find it?
Sorry, I'm not a materials guy. I don't know exactly how the chemistry works, but
Where you mine it, where it's found on Earth.
I think we have reserves in the US as well. Yeah. It's not a rare earth material.
Okay.
Yeah. There are other zinc-based technologies also that are being explored. And I know that PNNL is investing a lot in vanadium redox research. So there's a lot of work going on, and we are hoping that it'll pick up. I was talking about molten salt storage to assist concentrated solar. So that is not a not an insignificant percentage, as you can see. So strangely, lead acid is still a player in the field. Okay. But anyway, moving on. Here are some challenges and opportunities using storage. And unfortunately, a lot of pumped hydro storage facilities are being decommissioned because of their age. Some are being rebuilt and renovated, but some are being decommissioned. And you need certain specific geographic features to build them, so you can't just go about building them everywhere. Okay. But as I was saying, recent times have seen enormous investment in grid scale storage technologies, and I'm hoping that we'll see some demonstrations with these soon. So let's talk about the impact that storage has on the system in terms of improving reliability. And I'm going to try and also give you a flavor for what reliability means on the grid as I go along, okay, using a very simple example. But here's the problem of sizing storage for reliability. Can we determine the amount of storage required to meet a specific level of reliability? Excuse me. And now with storage, because it's an energy limited unit, you have two elements to the capacity. Power capacity, that is how much megawatt capacity it has, how quickly it can deliver the power, at what rate it can deliver the energy, right? And energy capacity, just how much energy it can store and deliver. So we need both aspects of this. And then the bigger question from here, can we go to determining how much storage we need to mitigate variability of, say, something like wind? Okay, and I'm going to try and give you a flavor of how we approach the problem, and how we went from one to the other without going into the details. But if you ever need to look at the details, these are some of the key references in that area. And by the way, if you look up my website, I'm very easy to find on any search engine. Okay, you'll find all my journal articles available on my website for download. So now think of, so I'm going to try and give you a flavor for this notion of reliability and availability. Okay, so think of trying to improve a system or taking a system with availability A0 and increasing its availability to A1. Okay, and so what is availability? Okay, it's a probability. It's associated with the probability of being able to serve that purpose. So, if it hasn't failed to meet this purpose, then it's said to be available. All right. So then think of this very simple example. Suppose you have a computer, a desktop computer, not a laptop, and you want to increase its availability from A0 to A1 by using a UPS. You all know what a UPS is, right? An uninterruptible power supply. Okay. And you want to try and determine how to size that UPS. Okay. And what are A0 and A1? A0 is the availability of power from the grid supply, from out the wall outlet. Okay. And you know that that's not 100% reliable. So you want to increase that availability, recognizing that your computer probably needs more reliable power than the light bulb, right? You want to increase it to A1 using a UPS. So A1 is the total availability you get from both the grid supply and the UPS. So first we define the unavailability reduction ratio. And here's an example to give you a feel for this. So and reliability is often talked about in the industry using nines. Okay, so this probability is called 3 nines, and this is called 4 nines reliability. So if you want to go from 3 nines to 4 9, then alpha is 0.1. So what you have here is alpha is the new availability. Sorry, new unavailability. Okay, 1 minus the availability gives you the unavailability. So alpha is the new unavailability divided by the old unavailability. Okay, or the numerator is the target unavailability. So this is the unavailability reduction ratio. Now, for those of you who have worked with probability and stuff, this is very familiar language. Okay, so SF is the event that your utility supply has failed. There's no power coming out the wall outlet. L is the event that the critical load, which is the computer, experiences a failure of supply. That is, both the utility power is out and your UPS has run out of battery. Okay. TA is the length of time for which your UPS can feed your computer. Okay. R is the random variable representing the downtime of the utility supply in this case. Okay, and this is a random variable because sometimes the utility comes back quickly, sometimes it takes longer, and so on. And this is the probability density function of this random variable. Okay, now I'm not going to go into details, but using this, it can be shown that the time TA can be determined from this integral equation. Okay, and why do we need TA? To determine the energy capacity of the UPS. Okay, what that means is, if if your computer is drawing, computer plus monitor is drawing 200 watts, then you need a UPS that can supply 200 watts or more, right? But for how long? And if you want to increase the reliability of supply by a certain amount, which you've defined as alpha, okay, then that how long, which also tells you how much energy is stored in the UPS, is given by PL times TA, right? So if you want UPS to sustain your computer for 4 hours, that's 200 watts times 4 hours, right? Okay, now it's easy to calculate TA or solve this integral equation for well-known distributions like exponential and Weibull and log normal and things like that. But if it's unknown, you can apply this equation, and we've derived the equivalence between these integral equations in one of those references that I mentioned. But we won't go into the details. But this shows how we can compute that. But now let's get to the real point I'm trying to make. How do you size it for the grid? Okay, when you have a wind farm and you're trying to make it dispatchable using a storage facility, then how do you calculate things like alpha, for which you need A0 and A1? And what is PL? Okay, now for the computer, we said that PL is the load that the computer draws, but on the grid, you can't say that the battery has to have as many megawatts as the total load on the grid. That would be absurd. So how do you find the megawatt size of the battery? Okay, and how do you find TA? That will give you the energy capacity. And through our research, we found this, that the megawatt size can be found from the difference between the nameplate capacity of the wind farm and the capacity value of the wind farm. And this was a fascinating find, because before that, when we were researching into this and reading up papers, we read a bunch of papers where they said, we ran all these studies and found that the capacity of the battery must be about 75 to 80% of the nameplate capacity of the wind farm. We don't know why, but, and not one, but multiple resources said that. And here's the satisfying part is that my research led to this, which explains it, because if the nameplate capacity is 200 megawatts and your capacity value is about 25% of that, which is 50 megawatts, then you'd need 150 megawatts of battery or any form of storage. And that is because of this difference. So it was pretty cool to be able to explain that away, okay, mathematically. And in terms of duration, we can apply this using the assumption that R is the mean downtime of the supply without the battery, okay, and this will give us the size of the energy storage in terms of number of hours. You multiply that by this, you get the energy capacity. So we ran an example, ran this idea on this test system, the IEEE reliability test system. I don't know how many of you are familiar with this, but this is used fairly frequently in the reliability space. And we augmented the system. We tested it on several locations in the system, okay, and we added 200 megawatt wind, okay, which had 100 Vesta V90 turbines, each 200 megawatts. Okay, MTTF stands for mean time to failure, and MTTR stands for mean time to reliability to repair. These are typical ways of representing the reliability of equipment. Okay, and we use some wind data set for which we found the correlation between the hourly load variation of this test system to be this, between the hourly load variation and the wind speed variation to be this much. So using the methods that I said was just talking about, we got this target LOLP at different locations. So we didn't put the battery at or wind farm at all these locations. We identified 5 different locations to test it at, and for each study we put it at one location. So we tried at 18, 13, and so on, based on where the wind was able to help the system the most.
Is the loss of load probability, right?
Yeah, so LOLP stands for loss of load probability, or there's also the unavailability. Okay, and so we started out with this target LOLP, and then we found that if you the capacity value of this wind farm at that location was 43.5 megawatts, so the power capacity of the battery had to be this much. And at each different location, as I said, this alpha would vary. So this how alpha changed over different locations. And in each study, we calculated the alpha, the TA, we rounded it up to the next hour. Doesn't make sense to use fractional numbers there. Okay, and then we sized the energy capacity as a product of this and this. And then we ran the simulation again and found that this was the reliability of the system for this 200 megawatts of wind, and this kind of battery, so many megawatts and so many megawatt hours at bus 18, and at the other buses, you get the idea. So you can see how well the target reliability matches this. So this was a satisfactory conclusion, and we felt that it was interesting that the theory explains some past observations. Now I want to take a few minutes to quickly give you a sense of the impact on frequency regulation. I won't go into a lot of details, but you do know how we keep a constant frequency of 60 hertz on the system, right? By using the energy stored in turbine generator systems, which are conventional generators with large turbines and large generator rotors, and they have a combined moment of inertia of J, and you know that when it's spinning at a certain speed, say 60 hertz, which is 377 radian per second, so half J omega squared is the rotational energy, kinetic energy stored in the turbine generator system. Okay, now what happens is you have mechanical power going into the turbine from, combustion of gases in a combustion turbine, steam going through the turbine in a thermal steam generator, okay, and so on. So that's the PM, the mechanical power that goes in. And though you can control this, it is not instantaneous control. It takes some time to respond, okay? But you know that electrical load, PE, is changing almost constantly, because at any given point of time, somebody's switching on a load somewhere, maybe a light switch or a motor or something, or even if they're not doing it consciously, an AC might be kicking in sometime, another one might be, might have stopped running at another part. So PE is constantly changing, yet the frequency remains stable at 60 Hertz. How do we do that? Because every time this is lower than this, the excess energy, the required energy, is sucked up from this by slowing down the generator slightly. And when we have so many generators across the grid, the slowdown is practically imperceptible. Okay, but if we didn't have enough generators like this, then slowdown would be perceptible. Okay, so you would feel that dip in frequency. Okay, and conversely, if this drops, then this generator speeds up a tad bit. Okay, again, if the inertia across the grid is high enough, you won't notice that pickup in the speed. It's going to be very, very tiny. Okay, so this is how we maintain frequency in the grid. But we know that variable resources supply very little inertia. And as they displace conventional resources, what happens? So we ran a bunch of simulations. Okay, so let me explain this graphic. This blue curve is the response to 10% change in load on a system without any displacement of conventional generation, that is with no renewable generation and no gas turbine. And I'm coming to gas turbine in a minute. Okay, this is the time axis, and this is the frequency deviation axis. So you see how the frequency deviates a little bit, oscillates, and settles down on the blue curve. Okay, now if you have a 20% inertia reduction as a result of displacing some of the conventional generation with wind or solar, then you see the green curve. So you can see that the deviation is a little more, and it takes a little longer to settle. Okay, now why did we look at the effect of gas turbines? Because gas turbines are being built a lot to, a lot of gas turbines are being built all over the system to provide ramping capability. But do they help with inertia? If the gas, so this curve is with a gas turbine that has a high ramping, this curve is with a gas turbine that has a high ramp rate, okay, high ramping capability. And you'll notice that the deviation is somewhat large, but it settles fairly quickly. But if the ramp rate is not high enough, then the deviation is large, and so is the settling time. And we've summarized that here, and this is basically what I just said. Okay, and this is the reference where we've published a bunch of these studies. And so what can we do? Can we use storage if we have such displacement, and can we replace this inertial storage with something like a battery or other form of storage? Okay, and the symbol here is a wind turbine being interfaced with an inverter to the grid. Okay, and we provide a little storage at this point of interface. Can we do that? It's called synthetic inertia or virtual inertia. Okay, and so here are some of the main references. Again, these are available on my website, and I'll tell you how we went about building this model. I won't go into the details as much as I did with the reliability business. Okay, but most of you folks may be familiar with the notion of optimal power flow. We use this constantly on when we are operating the system. Okay, and the objective could be reduction of fuel costs, or it could be maximization of social welfare in a market situation. And if there are electric markets, but whatever it is, the problem constraints are fairly similar. We have the power balance constraints, which can be expanded to this. So this is a more detailed representation of this. And then we have some equipment capability constraints and voltage magnitude constraints, okay, or these are also called security constraints. And then we have some transmission constraints, how much power can be transmitted over certain lines. We have spinning reserve constraints that we need to keep a certain amount of margin, and so on. And in the end, what we added was a set of frequency excursion constraints. So this one, which we represented mathematically like this, which we built using what is known as a load frequency control model. And I'm not going to go into the details of that, but this paper explains how to do that. So conceptually, what we attempted to do, we said, can we size storage? Can we come up with the size of the battery needed to mitigate this variability at a particular location or over the grid? Okay, so you have a certain amount of generator inertia, which you can lose either from generator failures or through generator displacement by including renewable resources. So your inertia goes down. But using the operational constraints that I mentioned, you can identify a minimum required inertia. Okay, can you calculate how much inertia you can get? Yes, if you can come up with a probability distribution function, you can calculate the expected inertia here. And if you take the difference, you'll know how much inertia must be compensated for by using energy storage. Okay, so and that is described in this fairly recent publication. Okay, so if you want to know a little more about what we did, we calculated what we call the probability of synchronization. And we got this from the probability distribution of the load and the probability distribution of system outage states to get the probability distribution of what is equivalent load. And then from that, we deconvolved one generator at a time to get the probability of synchronization of each generator. And it turned out that the probability of synchronization can be, when you look at the definitions, it's very close to the concept of capacity value of that generator. Okay, but anyway, so we got the probability of synchronization, and based on that, we built a distribution curve for different generators. And so the probability of getting so much inertia, so H is a measure of the inertia, okay, is this much, okay, from every generator. And from using that, you can get the expected inertia. And as I said, if you take the difference, as I showed here, you get how much inertia you might need from energy storage systems. And so we did this, again, using a well-known test system for dynamic stability studies, okay, dynamic studies and stability studies. That's the IEEE 39 bus system, also known as a simplified version of the New England test system. And we looked at 3 cases with different wind penetration levels and different frequency deviations that we allowed. Okay, we found that if we allow a large enough deviation, even without renewable resources, we may not need synthetic inertia. Okay, but if we tighten up the frequency deviation limits, then the tighter it is, the more storage we need. Okay, so what happens with this system if we have 8% penetration of wind, which is what we have today, approximately? Okay, so again, if the limits are loose enough, we don't need it, but we still need some amount of storage. But if we do want to move to a future with 20% wind, then even with fairly relaxed frequency deviation limits, and the frequency deviation limits are regulated in different countries by the regulatory agencies. Here it's NERC, or the North American Electric Reliability Corporation, that regulates our limits. But we can take the rate of change of frequency and the amount of storage that we just talked about, the inertia, and convert it to the size of the storage unit that we need. So for different cases, this inertia that we need from batteries can be converted to megawatt capacity of the batteries. Okay, so this is how this was our approach to sizing it. So anyway, I'm ready to close out my talk. As I mentioned, renewable resources present complex challenges, and we touched upon a couple of these challenges and how to mitigate them using storage. Now, competitive markets and smart grid technologies are pushing us closer and closer to operating margins, and which means we have to be more responsive and be more creative in coming up with solutions that give us the amount of reliability that we've been accustomed to. Creative ideas are emerging, but they'll need support from regulatory bodies. Okay, and if that doesn't happen, the industry will not adopt it. In the meantime, as I pointed out, there's tremendous thrust on deployment of storage technologies, transmission upgrades, including flow control technologies and the like. Okay, and we need to keep in mind that aspects of energy assurance are intertwined with concerns related to natural resources, sustainability, etc. And an example that I mentioned is hydropower, for instance, where so far we didn't think about its impact on natural resources, but research is showing that some of the impacts are not very positive. So there's a lot of environmental lobbies and things like that. So we have to deal with a lot of complex aspects as we keep up with the emerging needs of the grid. With that, thank you for your attention, and I'm happy to take any questions. Good.
Thank you for your interesting presentation. So my question is,
yes,
if there is a limit of the degree of penetration and to where this solution of synthetic inertia can be effective or not. I mean, if we consider a high integration of renewable
yes,
with energy, for instance, is still synthetic inertia feasible to be used in a
That's a difficult question, okay? Because I'll tell you why. There are people who believe that, for instance, that we can go to 100% renewable portfolio, but I just explained the challenges, right? So there are some who say that yes, we don't have all the solutions yet, but with things like storage and synthetic inertia, and with generation following and stuff like that, we can still move to a 100% renewable portfolio. We might have to sacrifice a couple level, sacrifice a little bit of the reliability that we are to. But hey, if you're rich enough, you can afford to buy bigger batteries, okay, and maybe your own generators and deal with it, okay. And then there are some that say that, hey, if you want the economics to make sense, at least in the present regime, then we cannot go beyond 30-35%. Okay, because we do need stable grid level resources to provide affordable power to the public and reliable power to the public. So there's all kinds of opinions out there, and I'm not ready to take sides.
Thank you.
Yes.
Yeah. Oh, so you talked about using batteries and designing them for inertia.
Well, it's when I said storage, I mean generic storage.
Okay,
at the grid scale, I was fortunate enough to meet the professor from New Zealand, Maria Skilla-Kazakos, who was the original inventor of the vanadium redox battery. She felt that vanadium redox is very good because it can deliver short amounts of energy, small amounts of energy over short time ranges very quickly, because you don't need the flow to happen right away. But if you need it over extended periods, you can start the pumps and get the electrolyte flowing. And so with one technology, you can cover all time periods that we need to meet variability and frequency response type approaches, okay, type scenarios. The other thing is So that's on one end of the spectrum. On the other end of the spectrum, a few years ago, PJM, which is the largest ISO in North America, they felt the need for frequency regulation and said we'll pay out very lucrative amounts of money in the frequency regulation market. So a bunch of people just built lithium-ion battery facilities to be able to sell, and they recovered this money really quickly because the payoffs were very lucrative. But those were small amounts, and they were not providing as much from one resource as PJM wanted. But a bunch of them made a lot of money out of this. So, well, I don't know if it's unfortunate, but now the payoffs have gone down a little bit with other resources stepping up to take up the slack. Okay. And even though MISO has a frequency response market too, it's nowhere near as lucrative. Okay. So there's all kinds of dynamics at work here.
Sure. So your ESS is how I think you actually talked
So
about.
I just, ESS, energy storage system, and I refer to a generic
Sure, okay,
ESS.
so
Yes.
I guess my question is, though, I've also heard about grid forming and grid following inverters.
Yes.
How would that, how does that relate? An additional solution, or
So
how do you see those fitting in?
So those are different kinds of inverters based on what their role is in interconnecting the necessary resource to the grid. Okay, and they're trying to build some of these features, some of these response capabilities into these inverters. But for example, one of the earliest things they tried building into inverters was the droop capability. Okay, so they called what they call a synthetic droop. Okay, and so they're trying to build these inverters so they can respond the same way as conventional resources work. So if you have to emulate conventional resources, inverters definitely don't have the capability of storing energy the way conventional resources store rotational energy. Okay, so then what do? You need synthetic inertia to work with it. And your question reminds me of a question one of my most recent PhD graduates, who's now with Sandia, asked me that, Dr. Mitra, I keep running into all these people who said, oh, inertia is no longer going to be important, okay, with all these power electronics coming in and all these grid forming inverters and grid following inverters coming in, we won't need inertia for very much longer. And I said, yes, you won't need inertia as a physical entity, but the spirit of inertia you'll continue to need, okay, no matter what. Yeah, that is never going to go away, because balancing between load and generation on an instant, on a millisecond or microsecond by microsecond basis is always going to be a challenge, because neither is static. Okay, and the need for balancing them is never going away. Inertia of conventional generators used to be something available to us in the past. Okay, and I see this extending into the next 50 years at least. But even if they go away 50 years from now, the need for the spirit of inertia, as I called it, the need for a storage-like device or something that can store energy in the short term and in the medium term is never going to go away. So to that extent, inertia is never going to go away. Yes.
Well, thank you very much for providing this very intriguing talk. I really enjoyed the presentation and found it very interesting.
Yep.
So I would like to ask you about how this optimal size of the batteries is going to impact the transmission grid, the requirement of the transmission grid.
Yeah.
I think you already noted in your slide that we need.
If you're going to ask, are people doing it yet? Nobody's doing it yet, because
right. So my question is more of a hypothetical perspective. So
yes.
If we follow this optimal investment in this optimal size of batteries.
Yes.
Because one of the largest challenge in large, high renewable penetration is, procuring the enough transmission grid capacity as well.
Yes.
So I wonder how this sizing of the battery can impact this optimal investment or the optimal sizing of the transmission grid?
So, okay, so you open up an interesting discussion. Have you heard of SATA? Not the USB SATA connection, but sorry, not the computer interface, but storage as a transmission asset. Okay, there's nothing new about it, but it's a new term in the grid space. Okay, and I say it's nothing new because in spirit it's not doing anything new. But instead of installing this to support generation, you can as well install it to support transmission. For example, when at the end of a transmission line, which occasionally gets congested, you can install storage to relieve the transmission on that line. Okay, so that is an example of storage as a transmission asset. Okay, but and if you draw boundaries around it like that, then it's easy enough to use some of the logic that I just applied to come up with the size of that storage as well. Okay, now make note of the fact that the kind of storage I was talking about is at a grid scale, at fairly large scale. And are we ever going to install it on that scale? No, never, because storage is never going to be the only solution. Remember what I was saying, that we are probably going to strike a balance between storage and aggregation and generation following somewhere. So you will never need that kind of storage. But the relevance of my methodology is in that if you can say that, all right, this is the kind of mix I'm going to try to achieve, then this is how much storage I need based on these ideas. Okay. At the same time, if you want to say that, okay, transmission is going to cost me so much, okay, generation following technologies is going to cost me so much. I know it's impossible to boil it down like that because there's a lot of consumer participation there as well. It's going to cost me so much, and storage is going to cost me so much. How much? What is my minimum cost optimal balance? There you can apply some of these ideas. So that's the value of the methodology that I outlined.
And speaking of which, I think that living in this emerging world, we often take energy for granted.
Mm-hmm.
We use it, and we never expect that planning for generation sizing is that complicated with all kind of technology. I want to ask you one thing, that you have used sizing as part of the ballpark to optimize the in terms of adequacy of the system.
Yes.
Have you thought about EV has been widely promoted with the federal government now
Yes.
to say that make predictions or load prediction of generation very difficult in that both end, because right now you only talk about the generation part of that.
Yeah.
There is the moving battery, moving storage that could be charging or discharging
Right.
on that span. In just imagine as part of the state of Michigan right now,
Yes.
we have growing number of electric vehicles. By the way, ERiSe Michigan just approved that EV center from one of their state operations. So they have
Right.
$130 million on that research center.
Mm.
Have you seen that, how that's going to make this planning so much complex?
It is going to make it a lot more complex. So your first question was, have I thought about it? Yes, I've thought about it a lot. Have I tried to do anything with it? No, because there are many moving parts to it.
Yes.
Pun intended. Because, you have to think about societal response. If I buy a $30,000 car, out of which the battery alone costs $10,000, okay, and I know that the life of this is going to go down dramatically with if I cycle it too much, would I ever connect it to the grid under two-way bidirectional flow? I would not, right? Until there was a mechanism for the grid to pay me so lucratively for use of my battery that it makes it financially, economically viable for me. Okay, but if the grid has to pay me that lucratively, then will the grid make money at the end of the day? Maybe not. Well, at the end of the day, the grid will collect the money from the consumers, but it will actually make it a lot more expensive. And then there's all this huge amount of uncertainty. Yes, people have tried to model these things, stochastically and stuff like that. But I have, and I've read some of this work, but let's just say I'm a little distance away from being convinced that we have a viable pathway to that. When we do, and that has to be enabled by regulation and
Yes.
public policy, then I'll come up with a model. Because then I'll know how to model it. But until then, I'm not convinced with all the models that are out there. I don't buy most of them. So that's my response.
Any other questions from the audience?
And
Well-
what I just told you about me as one consumer, there's only one part of the equation. There are a lot of other complex variables in EV technology, and even now, those who have EVs understand the pain of range anxiety, because we are still many years away from where we will have reliable
I understand that.
charging locations on the grid.
The consumer behavior part is one thing, and
Yes.
like California have set out a very ambitious plan for banning selling the combustion engine car for
Yes.
2035.
I
And
know.
we will always wonder how this is going to affect the other neighborhood state that's
Yes,
going to get
my son just moved his Honda Civic to California, and he was taxed heavily for that.
So
Yeah,
anyway, so
yeah.
thank you for coming today. I appreciate
Thank
it.
you for interesting discussions and for hosting me.